Swayam Prabha. Digital India. Educated India.
Good morning. One thing I love is interruptions. So please keep interrupting me. Okay, so I have two lectures planned. One is a kind of a math lecture, and the second is a physics lecture. And the physics lecture will use ideas from mathematics, and they are not meant to be separate compartments. It's actually supposed to be one big lecture. So, and I'm going to discuss something which was dear to my heart at your age, which is the idea of probability, combinatorics, which is counting, which I still do counting problems. Even though I'm nearing 60 years of age, I'm still doing counting. Okay, except when now I count black hole degeneracy, but same thing. Still I'm counting. So the plan is to sort of discuss ideas from probability. Professor Balki did something, right? A little bit. Okay, so he told me what he did. So, and lecture 2 is an application of these ideas to physics, but and the title of this lecture is a tribute to Professor Balakrishnan, and it is, what can the answer be? Okay, so this the tribute is Professor Balakrishnan has written a huge number of articles for this magazine called Resonance. It was targeted for high school kids, but ended up being slightly higher level. But doesn't matter. He had a series of articles in that where he would pose a question, and through pure thought and putting in conditions, he would get the answer. So that's what we're going to do. We'll answer 2 questions in that process. Okay. So before I proceed, have you people done some probability in school yet, or it's 12th standard syllabus? Yeah. Or I mean, most schools finish 12th standard also by 11th, right? In your generation. In my generation, that never happened. Summer vacation after 11th was summer vacation for me. Lucky people. So okay. So what we will do is, again, I don't know if you people do experiments in school. That's also optional these days. But when you do experiments, you make a bunch of measurements. Okay, so let's say we were measuring some quantity x, and we do something like this. We do x2. Let's say we make 5 measurements, and from that we are told to do something. What would you do? So these are supposed to be the same measurement done 5 times, and what would you assign for the measurement then? The average, right? So the average or the mean is what we assign, but there's a little bit more information out there which tells you that we can estimate for the error, statistical error. There might be other errors. You might be doing something totally wrong and this is garbage. I'm assuming that's not true. So for the what would you use? Variance or standard deviation. Okay, so that's usually square sigma. The symbol used the square root of variance. Okay, and so some questions we would like to answer is why do we? How do things improve? So here I have done 5 measurements. we could ask, suppose I did 4 measurements, 3 measurements, 6, 7, what is the, I mean, why should we do more measurements? And the thing is, how, so one question to ask is, you know, the error change with the number of and intuition tells you that it should get better, that the mean will be a better representative. Of course, we can't do infinite measurements. So we will answer these questions in a very, very nice manner. And the thing is, mean is something we understand, but variance, etc., looks like there is some formula given. Why is that formula given? And this is something which in our education system is not emphasized. What is emphasized is, here is this formula, use it. You know, asking why, I mean, why are you wasting time is what people ask you, but actually the question of why some things are defined. By the formula. Okay. This is also one more thing which we will answer. Okay. So before we do that, so we need to set some definitions. So the key idea here is that of a random variable. Did Professor Balakrishnan discuss this? He defined a random variable? Okay, doesn't matter. I will also define it. Again, I will also not be mathematically precise, but to give you a feel for it. It's okay to, so the key idea is that of a random variable. Okay, so what does that mean? So there is some variable x which takes these values. So the standard notation, so the whole idea is that, so first thing is, you will define something called a sample space. Let's use some notation, omega, for it. Okay, so that is just a set of possible outcomes of anything. So Professor Balakrishnan did the tossing coins thing, right? So suppose we tossed a coin once, what are the set of possible outcomes? Heads or tails, right? So okay, suppose we tossed 2 coins. So there are 4 outcomes, right? So head, 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 tail, tail, head, tail, tail. But the problem with things like this, I mean, these are not, you know, nice representations. So what you do is you map the sample space to a bunch of points on the real line. Because if you have points on the real line, we know how to add, we know how to multiply. So those operations can be used to make sense of this. Okay, so that's the key idea of a random variable, is that you map your sample space into some nice measurable space, and for this lecture it will be real line or some subset of it. Okay. So x, you should think of it as a map from sample space to the real line. This symbol is just for the real line. Okay. So this is the random variable. Okay, so let's do some examples. So let's look, one coin toss. So how do you convert that? So a single coin toss. Okay, so then I can do the following map, that under X, H gets mapped to 1 and T gets mapped to 0. Okay, there's nothing special about 1 and 0, but you will see why I chose that. Okay, so this so instead of saying heads, you will say that you got a 1 and then, okay. So then this is the nice part of this is that if you have n coin tosses, then we will have sequences of then omega will get mapped. So there are 2 power n possibilities. Okay, and then so let's say that, and we will also use this index I. So there for every toss, I will have a random variable which can take 2 variables. So if I toss it n times, I get n random variables. Now you are the one, you have a puzzle look. So what is the puzzle? Gamma. Oh, this is RV. Good. I mean, bad handwriting, bad whatever, that happens. So these are the things that we have. And now the advantage of making this is, so suppose we want, I can construct now, since all my random variables take values in the real line, I can add. So it makes sense to add random variables. Okay, so let me just say that I define some random variable y, which is okay. Now I have a question for you. What are the values the random variable y can take? 0 to n, right? So y now, y is a random variable, not gamma v, rv, okay, that takes n plus 1 values, that is and what is that meaning of this y? What does it tell you? If y is 4, that it's the number of heads, okay? So y is counts the number of heads. Okay, so this is so you can see that we got some benefit by doing this. Also coming back to that one, the experimental thing, there we can think of again x1, x2, x3, x4, x5 are some random variable x taking for 5, so it's like x1, x2, x3, x4, x5 taking some 5 possible values. Okay, but the only difference there is that we divide by n. That's not a big deal. Even here I could have divided by n, okay, and tell you that that's the average number of heads. So you can see that there's one meaning that we get from this, but even that description fits the thing, except there the xi's can take a continuum. I think it's not like taking only 0, 1 and things like that. So here y takes only discrete values, but that we need not be restricted to such things. Okay, so I'm just trying to motivate that we have the definition of a random variable. Second thing is that we can do operations, which is to add them, but there's also, we can divide by some constant. We can also shift by some constant. So why is that? Suppose you are not interested, I want to, instead of 1 and 0, I could make it 1 and minus 1. Nothing wrong with that. Okay. So that would correspond to shifting by something and dividing by something. I'll let you work out. So if you give me some random variable x, I can create a new random variable which is some ax plus b, where a and b are some constants. So exercise for you is, we want, let's say x is the head, which is 1, 0, and the map should go to 1 minus 1 or something like that. Okay, you can see that there are values of a and b which will do the job for you. Okay, so these are like these transformation are called affine transformations. Okay, it's just a name, it's just this. Okay, so sometimes doing this will simplify things. Okay. Okay, so the point is ax plus b will be another random variable, and every time you occurrence of the thing, you replace it by, so there is some notation I use. There's a random variable, I use capital letter, and possible values of that would be these little lowercase letters, just standard convention. Are there any questions or comments? By the way, comments are also fine, because I probably, I mean, there's a huge gap between you people and me, not only in age, but in perspective of the world. So I might be saying things in wrong words or using wrong language. So I know that because my jokes usually fail. I haven't cracked any so far. But that was deliberate. Yeah. Yeah, then I would just say 1, 2, 3. There it is. Yeah. So maybe not. I mean, maybe not. That could be a more complicated. I mean, that's not the. Here it was very simple. In general, I mean, just there are only 2 parameters. You don't have. So in a toss of a die or tossing a die, I would just make it 1, 2, 3, 4, 5, 6. Those are the natural numbers to that. Okay. So there, I mean, but if you want to ask things like, oh, what about what is the probability of getting an even and stuff like that, so there's no reason to choose. Anything goes. Anything goes.
So, like for those complexes, do they try to define?
No. Nothing. No, I just said that I chose 0 and 1 because then y has some simple meaning. It need not. But the whole, I mean, you will see now that I will motivate a completely different choice of a and b. Okay. So now we are sort of ready to discuss probability. So what we have is some variable x, and that can take values. Okay, this set could be discrete, like the case of this thing, but it could be continuous. Okay. Or even combination of both. So it could be that your random variable can take values in some interval 0 to 1, say, and then there could be some discrete values outside the interval. That's also possible. Okay. That's perverse, but allowed. Okay. So the whole idea is probability is to, so I will write things initially for discrete, and then generalization, do the generalization for this thing. So you assign, so probability is an assignment of values pi which belongs to 0 to 1 for each xi inside X. So I'm using capital X in with two ways, as the random variable and also as the set. Hopefully you can, in the context, you will understand. Okay, for each xi, such that, what is the property I should add? Total probability should be equal to. Okay, so let's ask what is the probability that we would assign to n coin tosses. So okay, and let us, for a single coin toss, we won't assume that our coin is fair. Okay, so if the coin is fair, what is P? Half. Very good. Okay. So before that, before proceeding, there's one more idea which we assume, but I'll define it for you, that each of the coin tosses are independent of each other. Right? First, I mean, you do a first coin toss, you get something. The second coin toss result doesn't depend on the previous. Okay, so we're going to assume, so the notion of independence I'll make precise its properties a little later, but independence of random variables So if you have a bunch of variables x1, x2, so in this case x1 to xn are the n coin tosses, that the knowledge of any one of these guys doesn't tell you anything about the others. Okay, so that means the again, this is not a very precise, does not influence any other xj for all j not equal to I. Of course, j equal to I, it influences, right? It's the same thing. Okay, so this is the idea of independence. Okay, so let's go back to the coin tosses, and now you have to, I have given you the thing. So y is okay. So now the question is, what is the probability of getting m heads? Okay, and I'll write some notation for it. P, the random variable is y, taking the value n. What is it equal to? You told me Professor Balakrishnan did this. Okay, let's assume it's a fair die. So it will be n choose m. Yeah. So when p equal to half, that will become 1 by 2 power n. So this is the, So it's like this problem where there are, so this is the pigeonhole principle. So there are n boxes, and out of which we have to choose m to put heads, any random, right? And the order in which you choose, it doesn't matter. So it is like this. You just say head here, maybe head here, and whatever is empty becomes tails. Okay, so that is this. So the way to understand this is p power m is the probability of getting m heads, but it's important that we have to put 1 minus p, the others have to be tails. That simultaneously that has to happen. Yeah. Yeah, so NCM is like old notation. Old means we are talking about before my time also. Okay, so the modern notation, that's why I deliberately wrote this, because you are taught, we are taught like this, NPM, NCM, that's very old, English books going back to the beginning of the 20th century. So, but those books, some of them are still very popular. And also today we write m factorial this way, but you might see people writing this. So these are all antiquated things, and we have to use modern notation. Modern means now 120 years notation. Huh? No, it's not there. There is no symbol for that. I'm trying to think where I used NPM. Very rarely, except when I was doing calculations like the ones you do in high school. I haven't used it much. Okay, so this is what we get. Okay, so this has a name. This distribution is called the binomial distribution. Okay, does anybody know what is the mean of this? Yeah, that's why it's called binomial. Does anyone know what is the mean number of heads? If you don't know also, it's fine. So this is NP, and NP Q, I know people remember this as NPQ, but Q is 1 minus P, because P plus Q is 1. Okay, don't worry about this. This is a calculation. If you don't know also, it's okay. Okay. Okay, so now we'll have 2 more examples which I'll introduce, and then we will play some games. So I'll introduce something called the Poisson. Does everybody know the meaning of the word Poisson in French? Fish. So Mr. Fish, that guy's distribution. So the Poisson distribution, now the values of x is like ad inf. Okay, so it can take value 0, 1, 2, 3, 4, so on and so forth. And I won't motivate this. I'll just give you the answer, and it just says that Px of say m where lambda is some parameter. Is it normalized? Does it add up? It's not normalized? Huh? Ad infinitum. So 0, 1 to infinity. Ad infinity, it goes to infinity. Standard Latin expression, but okay. So this is what we have. It's called the Poisson distribution. Okay. So exercise. Okay. The exercise is the following. Take the limit I'll do this later, but in a physics setting. Take n to infinity, take p to 0, such that the product np goes to a constant okay. So now on the binomial distribution. So let's look at x value. Y takes values from 0 to capital N. We are now taking n to infinity. So now we see that the space of y becomes the same as this first observation. Correct? So the second one is that you do, so that takes care of this, but p is supposed to be very small such that np goes to a constant. And the constant, I'm calling it lambda. Okay. So if you do this, you get the Poisson distribution. So Poisson distribution is a particular limit of the binomial distribution. So now a question to you is, what is the mean of the Poisson distribution? You are allowed to look up what is the mean of the Poisson width. Yeah, you'll go there and do it. What about variance? It's again lambda. Because if p is going to 0, 1 minus p is 1, right? So this is again lambda. Okay, so nice. So is this at least you have some feel for what this is happening? But of course you can ask how is that exponential coming, etc. That's like taking a mathematical limit, which I'll do at the latter part of this lecture. I'll do that. Are there any questions or comments again? Okay, so the third example is going to be what's called the normal distribution. Okay, so this is going to be different from those because there it was all the values were discrete. Poisson is also discrete, but it is infinite, but it's only a bunch of points. Okay, so now x will be the real line. Okay, so now we can't talk about probability, but we can talk about probability density. So the idea is now, because so this is a continuous random variable. Okay, so so p of x dx is the probability of the random variable taking values in the interval Okay, so it's more like a density. P of x is not, so this is called a probability density. Now the question to you is, how do I write that the total probability is 1? How do we write that? It will be an integral now. Okay, so goes to is this clear? Nothing deep about this. So now to tell you what this distribution is, I have to give you P of x. Yeah.
Why do we go to minus? Why can't we start with 0?
That's a different, I mean, I'm normal one. Yeah. I mean, I can give you, yeah, I can say that, you know, there's something called an exponential distribution which goes from 0 to infinity. Okay. But the reason why I'm giving you the normal, you will understand. So I have to give you the probability to complete the story. Okay, so I have to give you suddenly I'm trying to remember if there's a 2 here or not. I should know this. Just give me a second. Okay. So this is a random variable. So I'll write, so what notation now. Okay, so mu for this is mu. The mean of this thing is mu. And sigma is sigma. Sigma square is sigma square. So it has mean mu and variance sigma square. Okay, so the notation is that it's a normal distribution with mu and sigma square. It has 2 free parameters. Okay, this means okay. So I'll give you one integral. This is equal to root pi. Okay. This is a weird integral. It cannot be computed by ordinary means. Yeah, but following thing can be computed. The square of it can be computed. So what you do is a trick. You don't do this. So let me show you how to do that. And so let I then I square this integral can be done by, yeah. So I'm giving you, I wrote a formula for you. Huh. Beautiful. Yeah, that's what I mean. I have like 20 minutes to say why. It's like coming attractions. It's like that. Okay, so there's a preview to, I mean, there's a reason for this guy is very special.
How did we get
That's what I'm. Yeah. That's okay. This is just an integral. But I square can be done. Okay, this is equal to pi. So there is some change of variables. You just say x square plus y square, square root of that equal to r, and tan of theta. Make some change of variables, you can do this integral. Otherwise you can't by elementary means. It just says that it's a random. If I say that this thing, it just means this is the probability. It has only two free parameters, mu and sigma square, and not very original notation, mu for mean, sigma square for variance. Okay, so this, and if you plot this function, that's nice, you can plot it. If this is mu, it peaks and goes like this. And sigma in some sense is the width of that thing.
Using like this method, can like other integrals which cannot be solved?
No, see, the thing about integrals is each integral has its own character, right? I mean, some you can't, I mean, not everything you can do by this method.
Can even e power x square be solved using?
E power x square diverges. You can't do that integral because at infinity it blows up.
And ln x e power x?
Ln x e power I, you're asking me all questions. I mean, I have to look at each integral and make a statement about that integral. Okay. So there's nothing, I mean, this is just that. So you don't, all I'm saying is you assume this integral and then you can prove that it's normalized. That's all. I am not asking you to derive it, but if you know, I don't think you people have done integration, right, yet? You have done multivariables? Okay. Multiple variables, some people would have done, I think up to one variable, but two variable, okay. So again, this whole stuff is not something you need to, all you need to know is memorize it if you want. Okay, good. So now the next 20 minutes, I'm going to tell you why this normal guy is important. It also tells us at the end of the day, we are a bunch of sheep. And we can all be modeled by a normal distribution. So the point here is that, so let's say that, so now we will look at, so why did I call all of us as a bunch of sheep? Each one of us is a random variable. We would like to think we are independent of each other, but our collective behavior can be modeled by the normal distribution. This is called the central limit theorem. Okay, so the idea is that we have x1, x2 up to xn, which are independent random variables. Independent, somewhere I lost track of where I was. Independent, identical random variable. Okay, what does that mean? It means that all of them the same probability density. Okay, which I'll denote by like this, or simply okay, each one is the same kind of random. So it's like our n coin tosses, each one was a random variable, but each had the same probability. Okay, and and let mu and sigma square be the variance, mean and variance of each one of them. Okay, only assumption for me is that sigma square is finite. I don't assume it's not something blowing up. It's some finite number. That's all I need. Okay, so So far I actually did not write the definition of mean and variance, and I sort of appealed to higher authorities, which is your textbooks in school. So I'm just making an assumption. I'm saying all of you are in some sense similar to each other. It's like that. If you want to object to that, that's okay, but that's in my assumption. I'm allowed that. No, I'm truly individual. I appreciate that. But what I'm talking about here is, so going back to the original start of this lecture, I did 5 things. We are assuming that it's the experiment is the same. So that's all. Okay. So now we are getting ready to answer why. And I need some notation. Oh, okay, I kept that. And here I'll follow what's called the physics notation. So if x is some random variable, and then I'll just define expectation value of x power m as follows. And I will, for simplicity, I'm writing it for the continuous variables, but need not be continuous. Then you replace it by summation. What is the notation used in your book? This is there. I mean, like E of, sometimes the same thing is, electrical engineers definitely do this. They write it as, it's just taking the, okay. So m equal to 0 is so you read this as expectation value of x power m. So it says that it's like the average values of x power m. So that's what it says. So it's think of taking, you don't want to go around creating a new variable which is x power m, you just write it like this. More generally, you can write it for any function of x. Any function, need not be just polynomial, monomial, anything. Is this notation clear? Nothing, nothing. Now I can define mean and variance. I don't know how mean and variance was defined for you people, but I will define it in a particular way. So some properties you can get from this is that, you know, just go back to the definition, it trivially follows. And what is expectation value of 1? 1. It's a statement that total probability is 1. Okay? Very easy, trivial statements, but worth, because I'll keep doing manipulations. So the advantage of that is you can see if you give, suppose f of x is some polynomial, you can write it as sum of monomials and use this and compute it for each monomial. Yeah, go ahead, ask. That's what I'm getting at. Okay, so I mean already I can give you one answer. The mean is, so mu that is answer 1. Answer 2, So what it says is that, so I could have written mu here. You take x and subtract away from the mean, okay, and then square it. That gives you the variance. Except I am not telling you why I am giving that formula. Okay. So here at least you can see short form for these two things. But there is something very there is a special property of mu and sigma square which generalizes to many more things, to an infinite series of things. But so while I'm at it, I'll define something called skewness. Okay. So I can keep defining so these are properties of P of x, and x to the power m can be thought of as moments of the probability distribution. Okay. So now the question is, why are we interested in, what is special about sigma square? Okay, that funny combination. How do you people compute variance? You seem to know that. How do you compute? How did you do? So you do like a statistical sample, right? So you're given, so let's say you got x1, x2, xn, like the measurement we did, right? So then you compute the mean, and from each one of them you subtract the mean, and then you take its squares and then take the average of that. So roughly this is what that is. For a sample in statistics, that's what you would do, but there's a probability version of that. It's the same thing. Okay? So I want to keep this. I don't know if I've answered your question, but at least it's some cute notation for what you already know. Okay. So now suppose we have two random variables, x1 and x2, and let's say that they are independent. What does that mean? So it means the probability of x. So you have to talk of joint probabilities, right? Where this takes x1 and this takes x2. So we'll write some joint probability of two variables, each taking values x1, x2. This is equal to it's a product. Okay, this is what independence means. If these are not, if x2 affects x1, you can't write it like this. This is the mathematical statement of independence. It says that the probabilities are separated. And from this we get some cool stuff. We get like this. They separate out, because you go there and put this joint, you would have written joint probability, but then it will separate out and the integrals will separate out, and then it is as if you are doing only x1 computation. It's very, it's just writing the definition, you get that. Okay, so this follows. So this is from the linear independence, not linear independence, just independence of random variables. This is what you get. Okay. So So small x's are possible values that x1 can take, capital X1. X2 is all the possible values capital X2 can take. That's all. So every time you change these values, this probability changes. To be discrete, continuous, nothing. This doesn't make any assumptions on that. Okay, now comes so these were all definitions and properties. Now we'll go back to that setup, and then I will define why this is the random variable. But unlike with this thing, these are identical to each other, and okay, that's what we have. And so we can, what we would like to ask is what is mu of y, that is the mean of y. Let's just do that. Some property like that I had written somewhere. It's just sum of the individual guys, nothing deep. But what is the expectation value of x1? They're all, I've written something, all have equal, they have the same probability distribution. That means they have the same mean and same variance. So what is x1 equal to? The variance of the variable, which is, sorry, mean of the variable, which is mu. Okay, this is very easy. Now comes the fun fact. This is not easy to prove. It's little work. So what it says is that mean is additive. So by the way, in this whole setup, I didn't have to assume that they were identically distributed. If they are different distributions, then it's just sum of the individual means. And what I'm saying here is also true, that variance is additive. So if you have two variables, say x1 and x2, and ask what is the variance of the sum, the variance of x1 plus variance of x2 is the answer. So now I will just show you how to understand this. Okay. So instead of doing very, very complicated things, I'll do the case of n equal to 2, and that by sort of iteration you can prove for this thing. Okay, so let's do easier rather. Okay, so let y is just x1 plus x2, n equal to 2. So let's ask what is expectation value of y square is, now substitute this. And you expand it. So it's x1 square plus 2xy plus x2 square. x1, xy, but they are independent of each other, so I'll write it like this. So we can see that it's not additive. Y square is not equal to x1 square plus x2 square, but there is this ugly piece here. Okay. So now, so what do we do about that then? Okay, so so then we compute this expectation value of y whole square. Again, what is this? Is x1 plus x2. So this is equal to okay, you look at this. So what is happening? If I take the difference of this, the cross piece goes away. And then you get this y square minus expectation of y whole square, which you can show is same as the other formula. It is the variance. is equal to variance of x1 plus variance of x2. That's what I have. Okay. Skewness, which I wrote, is also additive. Now you might think, ha, beautiful, then I just have to write x minus expectation value of x whole cubed and power 4, it will work. From 4th onwards, it's a more complicated object, but it exists. So there are objects which are additive. Okay, so these are examples of something called, these are called the cumulants. I have just given you the first 3. Okay, and the most important ones are the first 2 cumulants. Yeah. So I have to take call this 1, call this 2, and 1 minus 2 implies variance of y provided x1 and x2 are independent of each other. Identical is not necessary for this. For cumulant story, identical is not necessary, but what I want to say next, it is necessary. Okay, so it's a fun exercise to prove that skewness is additive. But now you will get many more terms. There will be 3 expectation value of x1 square times x and the other one. So you have to sit there and you will have a whole bunch of terms to write. And again, when you do put some factors and all correctly, there will be nice, beautiful cancellations, all the cross terms. What you want is, you don't want something which is expectation value of x1 times expectation value of x2 to some powers. You want those ugly terms to go away and get something which only depends on x1 or x2. And I'm claiming that skewness is one of them, the next one. Okay, and there is 1 at every power. Okay. So let's come back to our problem. Oh, I still have, I don't want to erase something, so I want to keep that, I want to keep that, I want to keep this. So I only have this part of the board. I'm running out of space. So what I will do now is the following. I'll try to, so given x1 plus x2, I want to write some variable y, but what I will do is I'll try to construct a different variable z with one following property. So let z okay, it looks very, very complicated, but what I want is that mean of z or mu z should be 0 and variance of z I want to be equal to 1. Just which one? Y is x1 plus x2 plus y is this. I'm using this freedom which we discussed earlier, and first thing observation is that what works is the following. So from y I subtract out its mean. Yeah.
So here do we want the, are we assuming the mean and the variance is 0, 1, do we want the,
I'm just choosing, I have some freedom. I have 2 parameters of freedom. Okay, I have 2 parameters, so I'm just choosing. I can, that's the best I can do. I can't do any more. So this is very easy to see that if I subtract the mean of y from any random variable, if I subtract its mean, it's like shifting its mean of the new variable to 0. But now I have to scale it in such a way, and so that would be by the various square root of the, so that will do the job. So A equal to 1 by square root of n sigma. So maybe I should even put, let's remind ourselves how many variables we took. Okay, so claim is proportional to 1 by root n, skewness. I don't have freedom now. A and B are used up, whatever is, okay. So, and you can, of course, because of this, skewness of Zn can be expressed in terms of skewness of x's, which is given to you. It's some asymmetry in the problem. And now comes the thing, final. So, central limit theorem, which I can state. Central limit theorem now be stated, limit n tending to infinity of Zn, take it to infinity, what you will see is that variance and mu, they don't depend on n. What happens to skewness? Goes to 0. In fact, there are higher cumulants, they all go to 0, okay. And then it says that the normal distribution of 0 mean and this is effectively your, okay. So, you can model. So, what it says is, even though it looks like this is a mathematical theorem, but what you will find is that, for very small values of n, like 3, 4, 5, you will find that you can model, even though you don't know much about x, you only told its mean and this thing, you can actually, you can work out, you can treat Z as if it's already normally distributed. So, this is the power of the central limit theorem. It says, this is what I said, the sheep theorem, as the number of sheep increase and going to infinity, and they're independent, they behave, all you care about is how an individual sheep's mean and variances, that's it. From that you can reconstruct anything. So, if you know for Zn, you can go back and ask what is that first thing which I started out with, x1 plus x2 plus x3 plus x4 plus x5 divided by 5, right. So, you can work out what its mean and variance should be, okay. So, the thing is that this tells you, so the mean gives you the average value, sigma gives you the spreadness, and skewness gives you the asymmetry. What this is telling you is that the asymmetry and all gets washed out, and it's enough for you to know only two sets of numbers, the mean and the variance of the initial. Everything else can be written. So, that's the power of the central limit, and that's why it's the normal distribution, because it's expected normally. Okay, so let's take a break and then we will do some application.